All right, guys, I'm going to do a little flip-flopping around here between a couple different PowerPoints. Just a quick review. Remember that my videos for 8.1, 8.3, 8.4 covers quite a bit of the 18.2 section here. So we're not going to use a lot of this. This is actually going to be kind of short. So just make sure you go back to those to review a couple of key points. So make sure you've reviewed the value for Kw, right? That depends on temperature. A couple of reminders that in pure water, the hydrogen ion concentration is equal to the hydroxide ion concentration. So all the pH values for the different temperatures, that table that I showed you, are all neutral solutions. So pHs are considered neutral because neutral by definition only means that the two concentrations, hydrogen ions and hydroxide ions, are equal. In the previous videos, I've also talked about how the relationship between pH and pOH, what that relationship is, and that pH plus pOH is going to equal the pKw. That's going to come in later when we talk about Ka and Kb. All right, we're going to solve some problems, but a couple of things that I want you to note is that we're going to talk about buffer solutions a little bit later. We're only going to look at examples that involve the transfer of one proton in terms of assessment. There are ways of calculating when you have like a polyprotic acid that has more than one hydrogen ion it can donate, but we're not going to work with those calculations. Calculations at pHs other than 298 can be assessed, so to think about what that looks like. And then quadratics, so the use of the quadratic equations, are not going to be assessed. All right, so let's do a quick practice problem. Let's see if you can do it. Lemon juice has a pH of 2.9 at 25 degrees Celsius. Calculate its hydrogen ion concentration, hydroxide ion concentration, and pOH. Okay, pause it, try to do it, and then I'll walk you through. All right, here we go. So hydrogen ion concentration is going to equal 10 to the negative pH. So we know our pH, so it's going to equal 10 to the negative 2.90. That's going to equal 1.3 times 10 to the negative third moles per decimeter cubed. That's our hydrogen ion concentration. Next is hydroxide. So remember that pH plus pOH equals 14. So the pOH is going to be 14 minus the 2.9. And that gives us a pOH value of 11.10. So now we've found the pOH. Last thing we need to do is find the hydroxide ion concentration. And so the way to do that is we plug it in the same way we did for the first one, hydrogen ion concentration. So hydroxide ion concentration equals 10 to the negative pOH, which is 10 to the negative 11.10, gives us 7.7 times 10 to the negative 12th moles per decimeter cubed. Okay, you could also do it a little bit differently. As a reminder, Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration. So we know that Kw is 1 times 10 to the negative 14th. And we also know, once we find our hydrogen ion concentration of 1.3 times 10 to the negative third, we could just plug and chug, and get our hydroxide ion concentration that way. All right, so right now what we're going to talk about is dissociation constants for a weak acid and a weak base, and kind of think about the relationship between Ka, pKa, Kb, and pKb. As you can see here, the relationship is this. This is a logarithmic constant for Ka. This is the logarithmic constant for Kb. All right. So if I were to write out the acid dissociation constant, if we have just a generic formula for an acid, the H stands for the hydrogen in that acid, plus some water, right? So this is an aqueous acid in some water. We have our hydroxide ion, and then we have the conjugate base over here. It's donated its hydrogen over here, right? So what would the equilibrium expression be? It should look something like this. But here's the deal, is that when you're looking at things like a weak acid, this concentration of water is really not going to change that much over the course of this dissociation. So we can really consider it kind of like a water constant, and therefore it's not involved in the equation, and so we can take it out by just kind of plugging it over here with our Kc, and it basically kind of just disappears, because that concentration is really not going to change unless you have something that has a really, really high concentration of acid, and that's not going to happen that much. So you get an equation for Ka as hydronium ion concentration times the conjugate base, all divided by your acid concentration. Okay? Now, how does this relate to what we call the pKa? Well, pKa is just the negative log of Ka. And the idea is that as the Ka increases, your pKa is going to go down, right? So Ka is going to increase as you move from a weak acid to a strong acid, and therefore, as you move from a strong acid to a weak acid, your pKa is going to increase, right? So as you increase Ka here, your pKa decreases. As you increase pKa that direction, your Ka decreases. Yeah? Now, what does this look like in terms of relationships of different acids? Here we have methanoic, ethanoic, propanoic. Look at the Ka and the pKa value and see if that makes a little bit of sense now. So 1.8 times 10 to the negative fourth, 1.8 times 10 to the negative fifth, 1.4 times 10 to the negative fifth, and there's the pKa values. Now, what I want to show you is how do you actually calculate something in here. So I'm going to hop over here, and I just want to make a couple of notes for you. So most acids are weak, which means that they only partially ionize. And that's why we're bothering to talk about this, and we just did this right here. So we figured out our acid dissociation constant. Remember that a large Ka, which is what I just said, would be a strong weak acid. A small Ka would be a weak acid, all right? What's kind of cool, and you don't have to calculate it, but I do think it's kind of interesting, is that you can actually calculate the percent of a weak acid that's actually ionized. It looks something like this, but again, you do not, I'm going to say that again, you do not have to calculate this for the IB exam. I just think it's really cool that we can do it. So let's look at this. Oh, quick reminder, I'm glad this slide was here. When you're thinking about organic acids, anything that has CHO, the donated hydrogen is going to be the one that's connected to the oxygen, not to the carbon. Now this should make sense when you think about bonding, but just remember, a lot of people seem to pull the hydrogens from the carbons. They come from the oxygens, right? That's part of what makes this work. So let's think about actually calculating a Ka value. All right, so I'm going to skip ahead a little bit. I'm going to give you some information. So here's a reaction of niacin breaking down. Niacin is a trace element that we need. If you don't get enough niacin, you get like weird skin lesions and stuff. If you were calculating something like this, I'm going to give you some of the numbers. The way you could calculate is using an ICE table, right? So if I give you that the niacin concentration is 0.020, at the beginning of the equation, we don't have anything on our product side. When we do a change, it would look something like this. And then at equilibrium, it should look something like this, right? This all should be pretty standard. From the given information, this is given information from a previous slide, not important to you. Just know that I gave you a pH of 3.26. So we can calculate that out to give us our hydrogen ion concentration, and then we can plug it in. So what we actually get at equilibrium is this, all right? And so we could plug that into our Ka equation that we just figured out. And when you do that, you can calculate out your Ka to be 1.6 times 10 to the negative fifth. Now the reason I show you this is because there is a little bit of a shortcut. Be careful using it, but it does actually seem to work consistently. So I'm going to show you that shortcut here in a second. Now, if the Ka for niacin is 1.6 times 10 to the negative fifth, can you find the pH of a particular molarity solution? You can actually. So here's what it looks like. Again, there's our ICE table, right? And so this time we're changing the molarity to this right here. And so we set this up exactly the same, right? Now what we're going to do is we're going to do this. Ka is products over reactants, right? So I'm giving you Ka, and you can plug in this quadratic here. And that's just super messy, and nobody likes to work with that. But we could solve it using quadratic. And so what we would get is something that looks like this. 3.92 times 10 to the negative fourth. Okay? What that equals for a pH, you know how to calculate this. It's 3.41. Now, if the power for your K is -4, -5, -6, you can actually use a little shortcut, and I'm going to show you how to do that right now. So here is how to use the shortcut. This is what we initially came up with, right? But here's the deal, is that this minus x is pretty much negligible. That change right here from our initial to our final is going to be pretty negligible. So we can actually just get rid of it, as long as this power is -4, -5, -6, okay? And so you can take this and then you can just solve for x squared. And when you do that, you get something that looks like this, 4.00 times 10 to the -4th, which gives you a pH of 3.41. Previously, I'm sorry, 3.40, and when we used quadratic, we found it as 3.41. So it does actually work, okay? I'm hopping back over. So Ka is directly related to the strength of the acid. The higher the Ka, the greater dissociation, and therefore the stronger the acid, okay? Now what about the base? Honestly, it's exactly the same. You just set it up considering a base, okay? So instead of creating hydrogen ions, you're creating hydroxide ions. But just like last time, the water concentration is not going to change that much, and so we just consider it like a water constant almost. And so you get a Kb of your conjugate acid, BH+, your hydroxide ions, and then your base, okay? Again, Kb is a direct measure of the strength of a base. Higher the value of Kb at a particular temperature, the greater the ionization, the stronger the base, yeah? Here we can compare a couple of different bases, and you can see that ammonia has a Kb of 1.8 times 10 to the -5th, whereas methylamine and ethylamine have larger values for their Kb. And if we go back again, remember, higher the Kb, the stronger the base. And we know that's true, okay? We're not going to worry about that too much. All right, so quickly, for a conjugate acid-base pair, and we've talked about that a little bit, you can actually do a relationship. We've already figured out what Kw is, but how do we relate that to Ka and Kb? Well, what's really cool is if we solve out for Ka and Kb, you can simply multiply those together to solve for and have those equal to Kw. And it would look something like this. These are the two equations we've already kind of talked about. So here's Ka. Here's what Kb would look like if in the context of the acid, right? So if we were actually to think about the conjugate base going back to the acid and to create hydroxide, you'd have a Ka and a Kb like this. Do you see those? See how those are all in the context of the acid, so it's all the same? When you put Ka times Kb, it would look like this. And that way you could cancel out your concentration of the acid and the concentration of hydroxide base. And then you get hydroxide ion times hydroxide ion times hydrogen ion concentration to give you Kw, which is really cool. So this is how you can relate Ka and Kb to Kw. So if you can put it all in the context of the acid, you could do it with base 2, but either way you'd end up with hydrogen ions times hydroxide ions to give you Kw. All right? And that is actually how we end up with a pKw of 14 as long as you're at 298. Yeah? And you can also extend that to say that pKa plus pKb is also 14. Yeah? So that's how we relate all those. We will do some solutions to solve for this, but that's about it. In class, we'll do some sample problems, but I'm going to do just a quick summary for you, really quick. Maybe not. Maybe not. I knew it was in here somewhere. This is the only thing I wanted to show you, which was the connection to topic 8.1, 8.3, 8.4, and a connection to a couple of options on buffers, which we'll talk about at the end of the unit. All right, thanks so much, and I will see you in class to work on some practice problems.